Well, I thought I'd start out by asking how many blacksmiths are in the crowd today? That's because I asked them to come. Now, how many people have a family story that one of their ancestors was a blacksmith? Anybody? That's interesting because a lot of times when I tell people I'm a blacksmith, they'll say, oh, my great uncle was a blacksmith or something. But I guess it's kind of fading away slowly. Of course, it was an important and common trade back in the early 1900s and before. I came to blacksmithing in 1982, as Ron just said, after leaving the graduate school of chemistry at Berkeley. So in 1982, I moved to the town of Gießen in southern Germany, the state of Bavaria, and I did a traditional 3-year apprenticeship and stayed for 3 more years as a journeyman. This is a picture of my boss and his wife in front of their house. And in back of the house, there was a traditional smithy that had some modern conveniences to it. But it was a very kind of quaint, charming environment with lots of old bits of iron and stuff around. It was just like the perfect place for me to fall into. But in 1988, I came back to the U.S., and I first set up my shop in San Francisco. That was 1990. In 2000, I moved to West Oakland, and that's where I continued to forge to today. I kind of think of my shop as a laboratory where I research forged forms and historical blacksmithing processes. I guess that's kind of a nod to my chemistry days. My shop has a lot of modern tools that enable me to make a little bit of money in the sort of plus category, like air hammers and a full machine shop. But my main interest is in historical blacksmithing, and that's especially the forging of woodworking tools and metalworking tools. I also have a small school, I call it Rod Academy, and I teach anywhere from private lessons to up to 6 students. I like to keep the classes small. Let's see here. So we're here talking about iron today, and that is, of course, the traditional metal worked by the blacksmith. The last common commercial forgeable metal to bear the name iron was wrought iron, and that was a soft, low-carbon form of iron which was last made in the 1800s, the late 1800s. The carbon content of that material was about 0.02%, very low, and that's by weight. There's a lot of nostalgia for the old wrought iron since it was soft and easy to forge. It did have its quirks, though. Let's see here. Nowadays, our low-carbon commercial form of iron is actually steel, and it's called mild steel. The carbon content of that material is about 0.2%, and it is pretty forgeable. That is, it can be formed hot under the hammer, but it's definitely not as soft as the old iron. But in the blacksmithing shop, sometimes you tend to mix up the terms and refer to that low-carbon material as iron. And iron alloys with higher carbon contents, I'd say between 0.45% by weight and 1.2%, have always been referred to as steel, and they've been valued much more for their higher strength and hardness. So let's consider why steel is such a prevalent material in modern structures, fixtures, and hardware. There's, of course, some very cogent reasons for that. One is that it has an exceptional combination of strength, toughness, and malleability. It can be formed and assembled by a really wide variety of techniques, and it's inexpensive, durable, and it's really readily available. However, for the blacksmith, there are an additional set of properties of hot iron that make it a quite special and wonderful material. Today I'll concentrate on 3 of those properties of hot steel, and they're linked to iron's essential role in historical handwork and I'd say the rise of industry, basically. One of the properties is that it has a very high or a very wide range of temperatures for forging. It can be welded together, like 2 pieces can be welded together in the common blacksmith's forge with no extra equipment, and it can be heat treated to a very wide range of hardnesses. So let's look at point number 1. The hot work temperature range. I would say that's about 2,400 degrees Fahrenheit. That's what you'd heat your metal up to. And you can keep working on that metal down to about 1,000 degrees. That temperature range is displayed in this piece of hot metal laying on the anvil there. From 2,400 degrees down to 1,600, you can do heavy forging. You can really change the shape of the metal drastically. A little bit lower temperature than that, as your piece cools down, you can smooth it and refine the shape. That would be down to about maybe 1,200 degrees. And you can straighten your piece before you put it back into the forge down to about 1,000 degrees, maybe even lower than that. There's one additional property associated with the temperature of the iron, and that is that it conducts heat rather poorly, especially considered to the predecessor metal in our history, human history, of copper or bronze. What that means is that you can heat a piece of metal up to almost the melting point and maybe 10 inches or 12 inches away, if you work fast anyways, you can be holding onto that bar of metal. So you can be hammering the end of it, holding it with a great deal of control, and that's part of what makes it easy to construct things in the fire. So the second point that I'd like to go over is forge welding. This is an amazing process. It's my favorite thing to do in the forge. And what it is a solid state bonding of two pieces of iron at about 2,400 degrees. What this is meant for blacksmiths and generally just people in general who rely on technology, handcraft, which all of us have for thousands of years, is that the blacksmith was able to make larger and more complex tools and implements than could have ever been feasibly done out of one piece of steel or iron. And the fact that both high and low carbon steel can be welded together has enabled blacksmiths working in conjunction with all the other craftsmen to develop beautiful, complex tools for a huge variety of historic trades. In the process of welding, the parts that are getting welded together are heated to a sparkling white heat. That means literally when you pull them out of the fire, sparks are just shooting off of them like sparklers a little bit. They're brought together and hammered together, which causes them to form metallic bonds between the atoms on each side of that seam. That means that electricity and heat can conduct across those pieces that are welded together now. And all of the atoms that are bonded across the seam are bonded to the atoms that were in back of them in the original pieces of metal. So you basically have what's pretty close to being a single piece of metal after the weld. Now, since iron oxide, which continually forms on the surface of the hot iron, would hinder this welding process because it's a solid and it would be stuck in between the pure iron atoms, a flux such as borax is used to dissolve the oxides. If you sprinkle borax onto yellow hot metal on your way to heating it up to white hot, that borax will immediately melt on the surface of the metal, and it does a really good job of dissolving iron oxide. So when you bring the two pieces of iron together to hammer them and press them together, the oxides, which were a solid, are now dissolved in a liquid phase, and they are simply pressed out of the gap. And that's what allows the iron atoms to come together at a very high temperature. So here is a video that shows this process. Jonathan, who's out, I think, at the tables there, helped me weld 2 bars of 3/4 inch thick square iron together. I'll just get that started. I'll narrate a little bit what's going on here. So I've got 2 bars of iron in a coke fire. I'm heating them up on the ends to get them ready for welding. You can't just lay 2 square bars together and weld them. You have to shape the ends in preparation for the weld in a process that's called scarfing. And prior to that, I'm doing what's called upsetting the iron, make it a little thicker, in preparation for the later hammering down of the metal during the weld. This is the beginning of the scarfing process. I'll just let you watch that for a minute. So you can see I'm tapering the ends out thin. And you'll see in a second how that helps blend one piece of metal into the other. So 2 equal pieces mate together like this during the weld. But they have to be a lot hotter than that. This is the step where I put borax on them. Take a little bit of the iron oxide with a brush there. This is a little better than 20 multame here. It's anhydrous, like industrial borax. So now they're going up to 2400 degrees or so. And then there's sort of a choreography of getting the weld together. There's a certain sound that tells me that these pieces are welding right now. But I can't finish the weld in one heat. It has to go back in probably 4 or 5 times to get everything finished. The weld is essentially done now, but the piece is very irregular, so the work after this is all geared towards getting the bar back to a nice straight square shape. And the flakes that you see coming off laying on the anvil are iron oxide. In industry where they produce tons of that stuff, they actually collect it and put it back to smelting because it's essentially pure iron ore. After this, we'll be using a tool called a flatter and a sledgehammer to make a much more even shape out of it. And there's the finished weld and the finished up bar, and you can see that there's almost no trace of the original seam left. So we'll test it now for you just to help you see like what a thorough bond this is. There's no modern specification for this type of welding. It's pretty much died out in an engineering sense, but it's still done by blacksmiths just who are really into the history of the trade. Hooray! Thanks. That piece of metal is out on the table. I had to shorten it a little bit to cut the weight down, but if you want to take a look at that, it's out there. Okay. So the next couple of slides are going to show historical tools which were forge welded together from several pieces of low and high carbon steel. And I think you'll realize that the modern versions of these tools are nearly always made of a single piece of high carbon steel. These are 2 Viking-style axes. They're each forged from 2 pieces of steel. I think I got a pointer here. The body of the tool from the back of the eye here up into the blade is low-carbon steel, soft. It's easy to form, and historically it was a much cheaper commodity. So cheaper, easy to weld, and easier to shape. So that's what you did most of the tool out of. And then in the front, you can see there's kind of a line there. That's the high carbon steel, and that was put in because it could be hardened and make a very sharp cutting edge that would last a really long time. So likewise, here's a hammer. Now this is made out of 3 pieces, and in this case, the body again was made out of soft steel or soft iron back in the day, because heavy punching operations would have been nearly impossible to do in a high carbon material. But the high carbon was necessary to have in the face, and the feature here called the peen, because they both had to take a lot of beating, when the hammer was used. But this next tool has to take the cake. It is called an old Bavarian anvil, and it's forge welded from at least 14 pieces of metal, 13 pieces plus of wrought iron, and 1 high carbon steel face that goes from the back end all the way to the tip here. And every distinct feature you can see here, like this foot, this buttress here, these features, this slab of iron, this horn, in the middle. Those are all separate pieces of metal that were welded together in Germany by guys with sledgehammers. And this next slide gives you a little insight into how that was done. And the next slide is the final process of laying on the high carbon steel face, and that clouds of stuff that you can that are coming up from the anvil and reflecting the heat. That's borax fumes. This is the hard part of the process. The owner of the company was Ernest Reflinghaus, and this picture is probably from the 1940s to the 1960s. Ernst Reflinghaus is the second guy from the right, and I visited that shop in 1987 and met his son. So the third process, the last process I wanted to mention, was hardening and tempering steel. And this is basically pretty much quenching the steel from about 1550 degrees Fahrenheit. Historically, steel was distinguished from iron by its higher carbon content. Even if they didn't know that it was higher carbon content, they knew the properties of that material, and it was difficult to make from iron and wasted or used a lot more resources, so it was more expensive. So steel might have been 0.45% carbon to 1.2%, and it was capable of being hardened for use as the cutting edge of like an axe or knife, or an impact tool, the face of an impact tool such as a hammer. To harden the tool, the steel part was heated to a specific incandescent red heat called the critical temperature, again about 1550 degrees. And it just turned out that that's where the steel lost its magnetism. So for at least 100 years, people have known to check for that temperature by testing it with a magnet. You can't harden the steel if you quench it at too low of a temperature, and if you heat it very much over that temperature, you're actually damaging the steel. So that was a good way to monitor the process. After the tool reached that temperature and soaked a bit, you quenched it in oil or water, and at that point, that steel was as hard as it could possibly get in that tool. But it was also as brittle as glass. To illustrate the quenching process, I'm going to show a short video of a Viking-style anvil, which includes the hardening process at the end. It starts by showing the traditional process of forge welding a high-carbon steel face with a mild steel body, and after the final shaping happens, it's heated to the critical temperature and hardened by quenching in oil. So this is the welding process. The sledgehammers all the way. After about 15 minutes of this, your t-shirt is completely soaked with sweat, like you could wring your whole t-shirt out. There's some finishing of the joint. By the way, there's a lot of heat radiating off this, so you can imagine that Bavarian anvil, 400 pounds of this. This is finishing the face, and then it goes to the fire. Oops, first it gets my name on it. Then it goes to the fire and into the quench. So, and we're almost done here. So, I'm sorry about that. So, after the quench, the tool was as hard as it could get, but as brittle as glass. And it's literally true that if you had a knife that was hardened to this degree and you dropped it, it would likely break into 2 or more pieces. It would just shatter like glass. To make the quench steel usable, it was tempered, and that means that it was reheated to a lower temperature, somewhere between 320 degrees Fahrenheit to maybe 600 degrees Fahrenheit, which took away some of the hardness, but it also took away the brittleness. And what the tool got in return was toughness and maybe springiness. And so the toughness trades off with the hardness, but you have to hit the right balance for a tool. A tool such as a chisel or plane blade would be quite hard because you're not expecting it to hit a rock or something in a nice piece of wood, whereas a hammer for pounding iron, you'd want it to be somewhat hard to last a long time, but if it ever hit something as hard as it was, you wouldn't want it to chip. A chip coming off the face of a hammer could cause really bad internal damage to you because it comes off like a pistol shot. I've heard stories of people getting steel splinters lodged in their abdomen and stuff, from working at the anvil. Not entirely safe. Now, the really wonderful thing about tempering for the blacksmith is that the entire range of useful tempering temperatures can be displayed as temper colors on the surface of the steel if it's polished before the tempering takes place. So controlling that exact process is really important when there was, fairly demanding specifications for the tool. Like you'd totally want your chisel, your plane blade to last a really long time. And like I say, you wouldn't be so concerned about chipping it. So you want a hard tool there. The colors displayed, the ones you can see here, give the blacksmith a really reliable way to temper his tool to the right balance. And in fact, if you think that 200 or 300 years ago, and in any case, in any just average smithy, there was no way to monitor a temperature on a scientific scale like the Fahrenheit scale or Celsius. So all they really had were these temper colors. But they're kind of beautiful colors. They're extremely characteristic to the temperature that the tool was raised to. And a tool would generally be tempered to a color like straw yellow or plum or midnight blue or something like that. And to conclude the talk, I'll just show you a couple of tools here where I thought the temper colors came out kind of nice. This is a Baltic style Viking axe, and the color I hit here was kind of a plum. And in fact, you can see the steel is the plum colored material on the front of the axe. That's the edge material, whereas the material just behind it, that's just sort of a pale gold, is the iron body of the tool. And the last tool is a Viking style type M axe, battle axe. And in fact, my friend John Kiernan out at the tables purchased this from me. It had this beautiful periwinkle type color to it, so I just had to take a picture. Anyways, that's the end, and I'd like to thank Anna Geyer for all video documentation.
Thank you, Jim. Don't take your microphone off yet. We may have questions for you. Does anyone have a question for Jim? There's one right there.
You said that after you finished your training, you spent 3 years as a journeyman.
Uh-huh.
What does a journeyman do? Do you actually travel around and look for work? Or?
Kind of ideally, that was kind of the best thing you could do, but I just stayed in the same shop. And I spent a year as in a woodworking shop because I wanted to learn how to make hinges and fittings and stuff.
Any other questions? Thank you, Jim.
Yep.
If you have any questions, then you...
one more.
There is another question. I'm sorry.
Hi. What is the difference in sound as the bars are welded together? How does the sound change?
It's something you pick up doing this for a long time, but it's sort of a dead, doughy sound that the material has. And it's a very subtle difference from when it's not sticking.
I have a question for you.
Mm-hmm. Yes?
Those colors, the tempering colors, are they part of just a surface color, or is it bulk? Does it go all the way through the steel?
No, it's a surface color. It's some sort of interference filter effect with a thin layer of iron oxide on the surface.
Because it has the same features as bubble colors, the same order of colors, I noticed. So an interference feature is kind of,
yeah. If you use some Scotch-Brite, it would be gone instantly. Yeah.
How do you make a living doing this?
Good question. Anybody have a job out there for me? I'm not the best go-getter when it comes to custom work, but there's a lot of custom work to be done in houses. You can make products, and teaching is helping a lot too. I feel teaching's kind of like my calling, because I really like learning stuff, and once I learn it, I really like other people to learn it.
So if this doesn't go along with those who can do, those who can't teach, this is those who can teach.
Yeah. And I don't know,
I like that.
can't sell jobs, you know.
Any other questions?
There's a table out just outside there if you want to look at some iron objects. I know the story behind all of them because I made all of them, and they all have something to say about early ironworking techniques.
And if you want to come up and play density blocks or take a look at some of the minerals, please feel free to come up and do that too. Thank you.